Hello and welcome to another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 6, Lesson 3 on summation notation. Right, so what in the world does this even mean? Let's get right into it and discuss what summation notation means. All right, now you know what a sum is, all right? Much of our work in this unit will concern adding or summing the terms of a sequence. To specify this addition, or to summarize it if you will, we will introduce a new notation known as summation or sigma notation that will represent these sums, all right? And you'll hear math teachers refer to this as both summation and sigma notation. Now the reason that they refer to it as sigma notation is that this strange looking symbol that looks kind of like a capital E is actually the Greek capital letter sigma, all right? And as you go further and further in math, for some reason, you'll see more and more use of Greek letters to represent particular things. S for sum, sigma notation. Anyway, let's take a look at what this even means. All right, so we've got this sigma notation, right? And then we've got this little I equals A at the bottom and an N at the top and f of I, which is just, function notation. And then it equals f of A plus f of A plus 1 plus f of A plus 2 plus ... all the way up to f of n. Now I is called the index variable, and sometimes it's an I, sometimes it's a J or a K. It's typically some lowercase letter in the middle of the alphabet. It always will start at an integer value, so never a decimal value, always an integer value, but it could be negative or positive. All right, and in this case, we're saying it starts at a value of A, and it always ends at an integer value of N, and it always moves in increments of 1 unit each time. So it goes up by 1 unit each time. All right, so that's pretty confusing, and you're probably like, I still don't understand what any of this has to do with anything. So let's take a look at exercise number 1 and get a sense for summation or sigma notation. Evaluate each of the following sums. Show the work that leads to your answer. All right, so let's take a look at letter A just so you can start to get a sense for this. I'm going to write this a little bit bigger on the board, so hopefully you can see it on your tiny screens. All right, so I've got this Greek letter sigma. I is equal to 3. Remember, it will always start at a whole number to 5 to I. So now what this is saying, all right, what this problem is saying is take this function 2 times I and plug in I equals 3. All right, so that's going to be 2 times 3, and then add to it, bump the I up by 1, so I goes from 3 to 4, and now you're going to have 2 times 4, bump the I up by 1 again until you hit 5, and now you'll have 2 times 5. So obviously then we just are doing some arithmetic. 2 times 3 is 6, 2 times 4 is 8, 2 times 5 is 10, 6 plus 8 is 14, plus 10 is 24, and that is the value of our sum. All right, and that's really it. But let's do another one together, because again, these things can be awfully confusing. Let's take a look at letter B, where I will again write it a little bit larger on the board. So again, I'm just trying to write this bigger so that you can see it. All right, here we're going to have our index value variable, which is k, start at -1 and go to 3. And we're going to sum k squared. All right, so in other words, we're going to start at -1 and we're going to square it. We're going to increase that by 1, which means we go to 0, and then we're going to square it. Then we're going to increase that by 1, which means we go to 1 and square it. Increase that by 1, which means we go to 2 and square it. Increase that by 1, and that means we go to 3 and square it. So there are more now terms in this sum than there were here. Here there were just 3 terms, term 1, term 2, term 3. Here we sort of have term -1, term 0, term 1, term 2, term 3. But now we just have to do some squaring. So -1 squared is 1, 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9, 1 plus 1 is 2, plus 4 is 6, plus 9 is 15. Awesome. Let's do one more of them together and then have you do a little bit of them on your own. Let's take a look at letter C. Again, let me write this up a little bit bigger. Here our index variable is J. All right, so we're going to start with j at -2, and it's going to go up to 2, and we're going to then sum everything that's 2 raised to the j power. All right, so we'll have 2 to the -2 power, then 2 to the -1 power, 2 to the 0 power, 2 to the first power, and 2 to the second power, and then we stop, right? So this is our starting value. This is our stopping value. 2 to the -2 is 1/4, right? 1 over 2 squared. 2 to the -1 is 1/2. 2 to the 0 is 1. 2 to the first is 2. 2 to the second is 4. Let's see if we can do this all in our head. 4 plus 2 is 6, plus 1 is 7. 7.5, 7 3/4, or 7.75. Let me just make sure. 2, 4, 6, etc. Yep, looks good. 7.75. All right, so this is just a way of basically expressing the sum of some kind of pattern, if you will. All right? What I'd like you to do is pause the video now and work through D, E, and F, and then we'll go through them. All right, well, D's kind of interesting because in this case, again, writing it just a little bit bigger, we have the summation starting with I equals 1 going up to I equals 5 of -1 raised to the I power. So we have -1 raised to the first plus -1 raised to the second plus -1 raised to the third plus -1 raised to the fourth plus -1 raised to the fifth. Now, -1 is an interesting number because anytime you raise it to an odd power, you get -1. And anytime you raise it to an even power, you get +1. So we're going to get -1 plus +1 plus -1 plus +1 plus -1. That's going to cancel that, which is going to cancel that, which is going to cancel that, and that's all going to just equal -1. All right, simple enough. Let's take a look at letter E. All right, in letter E, we've got the summation k equals 0 to k equals 2 of 2k plus 1. A little bit more of a complicated expression in there. So that's going to be 2 times 0 plus 1. Maybe I'll put all that in parentheses. Plus 2 times 1 plus 1. Plus 2 times 2 plus 1. Plus 2 times 3 plus 1. Give myself a little bit more room there. That doesn't look like a plus 1, so maybe make it a little bit neater. All right, let's see if I can work it out. 2 times 0 is 0, plus 1 is 1. 2 times 1 is 2, plus 1 is 3. 2 times 1 is 4, plus 1 is 5. And 2 times 3 is 6, plus 1 is 7. And look at that, it looks like I'm just adding all the odd integers. 1 plus 3 is equal to 4, plus, whoop, where did I make a mistake?
The limit's 2.
The limit, oh my goodness, yes. I went 1 too many. A hazard in this particular type of problem. I would have gotten it way too big. So we have 5 plus 3 plus 1, which is equal to 9. Excellent. Thank you, Joey. Yep, so we have 9. And let's do our final one, letter F, also a little bit more of a complicated expression. In this case, we have the summation starting at I equals 1 and going to I equals 3 of I times I plus 1. All right, that means that we're going to have 1 times 1 plus 1 plus 2 times 2 plus 1. Let's see if I can stop at the right point now. 3 times 3 plus 1. So that's going to be 1 times 2, which is 2. 2 times 3, which is 6. And 3 times 4, which is 12. So that's going to be 18 and 20. Let me just make sure that looks good. 6, 3, 4, 12, good. All right, great. So hopefully the idea here is pretty obvious, even if the point of why we're doing this isn't so obvious. Now, just as a side note, there are many situations in economics, mathematics, physics, all sorts of different applications where you need to be able to represent a really long sum but in kind of a compact way. And that's really why we use sigma notation. All right, for those of you who move on to both pre-calculus and calculus, you'll see sigma notation used a ton, especially in calculus and higher level courses that are absolutely essential for people who go into engineering and chemistry and physics and things like that. So let's keep moving. All right, exercise number 2. Which of the following represents the value of the summation of I equals 1 to 4 of 1 over I? All right, well, see if you can figure out which of those 4 choices is correct. Feel free to use your calculator where you see fit in this, and then we'll go through it. All right, well, let's do it. Again, let me write this out a little bit larger. One of the problems with sigma notation is that the index variable ends up being very small. So although on a worksheet it's pretty easy to see, on a video it may not be. So here we've got, starting with I equals 1, we've got 1 divided by 1, then 1 divided by 2, 1 divided by 3, and 1 divided by 4. Obviously that's just 1 plus 1/2 plus 1/3 plus 1/4. And of course, you can use your calculator to very quickly figure out what the fraction version of that is. I'm not going to spend time going through how to add fractions together. If you want to see that, feel free to visit some of our Math 6 videos. You know, that would be the level at which you're, last really adding fractions with like denominators and whatnot. But most common, graphing calculators can just sort of add these things for you and give you that final fraction. All right, let's keep moving on. Exercise number 3. Consider the sequence defined recursively by a sub n equals a sub n minus 1 plus 2 times a sub n minus 2, and a1 equals 0 and a2 equals 1. Find the value of the summation I equals 4 to 7 of a sub I. All right, well, let's kind of work our way backwards by first just taking a look at what's going on here, right? So that's sort of the new part of our lesson. Let's just see if we can understand what's going on there, right? What does summation notation tell me I'm supposed to do here? Well, it says start with I equals 4 and plug it into this formula, right? Well, if I put I equals 4 in here, that's A4. And then if I bump it up by 1, it becomes A5, and bump it up by 1, and it becomes A6, and bump it up by 1, it becomes A7. So what this summation is telling me is it's saying, given that I have a sequence defined recursively like this, give me the sum of the 4th, 5th, 6th, and 7th term. So what I'd like you to do right now is pause the video and see if you can use this recursive definition to produce A4, A5, A6, and A7, and then add them together. Pause the video now and see what you get. Well, let's make sure that we can read this recursive definition. This recursive definition says to generate any term, take the one immediately previous to it and add 2 times the one that's immediately previous to that one, or 2 of them before that, right? So in other words, A3 is going to be A2 plus 2 times A1. So A3 is going to be 1 plus 2 times 0, and that means A3 is going to be 1. A4 is going to be A3 plus 2 times A2, so that's going to be 1 plus 2 times 1, and that means A4 is going to be 3. A5 is going to be A4 plus 2 times A3. A4 is 3, A3 is 1, so that's going to be 3 plus 2, and that means A5 is 5. Let me just give myself a little bit more room here. A6 is going to be equal to A5 plus 2 times A4, so that's going to be 5 plus 2 times 3, that's 5 plus 6, and that's 11. I need one more. A7 is going to be A6 plus 2 times A5. A6 is equal to 11, A5 is equal to 5. So that's going to be 11 plus 10, or 21. Now, the problem just says to find the sum of A4, A5, A6, A7. So I want, maybe let's do it in red. I've lost my pen. There it is. I'm like, where is it? Got to be somewhere on the board, right? I want to add this one, this one, this one, and this one. Let me go back to blue. So this sum is just going to be 3 plus 5 plus 11 plus 21. 21 plus 11 is 32, 37, and 40. Let me just check that, and it does look like it's correct. That's it. Now, by the way, this is giving you a little bit of a spoiler or preview of where we're going to be going for the rest of this unit, right? So typically what we're going to be doing for the rest of this unit is actually adding the terms of a particular sequence to give us what's called a series. But don't worry about that terminology right now. Let's keep working with these problems. Writing sums in sigma notation. It's also important to be able to place sums into sigma notation. How we write a sum in sigma notation will often not be unique. And actually, I should really strike that and say how we write a sum in sigma notation will never be unique. In fact, there are often an infinite number of ways to take a particular sum and write it into this summation notation. So let's take a look at how we might do that in exercise number 4. Express each sum using sigma notation. Use I as your index variable. First, consider any patterns you notice amongst the terms involved in the sum. Then work to put these patterns into a formula and sum. Okay, so we look at this first example where we have 9 plus 16 plus 25 plus ... plus 100. So pause the video right now and take a look at those numbers, 9, 16, 25, and 100, and see if anything occurs to you in terms of what kind of numbers they are. Well, these are all perfect squares. In other words, this is equal to 3 squared plus 4 squared plus 5 squared plus ... plus 10 squared. And then this weird thing like that. All right, that means that I can actually write this in summation notation by saying, let's sum I squared, where I starts at 3 and goes to 10. And that's it, right? So 3 squared plus 4 squared plus 5 squared plus etc. all the way up to 10 squared. Okay, great. So maybe what I'd like you to do now is take a look at letter B and see if you can do this for yourself. All right, well, what do we have going on here, right? We have -6, -3, 0, 3, etc. And you might say, well, each one of these terms is 3 more than the last one. And that's definitely true, but that might not help us that much, right? In fact, what's pretty clear to me about this sequence is that the first term is 3 times -2. The second term is 3 times -1. The third term is 3 times 0. The fourth term is 3 times 1. And the last term is 3 times 5. So it looks like what we're doing is we're summing multiples of 3, right? Where we start with -2 as our first sort of multiple and go all the way up to 5. So we can say now that this is the summation I starting at -2 and going up to 5 of 3i. And that's it, right? 3 times -2 plus 3 times -1 plus 3 times 0 plus 3 times 1, etc. Okay. Pause the video now, look at letter C, and see if you can figure out what pattern is going on there, and then if you can put that pattern into a summation. All right, well, again, this one could be a little bit tricky, but 1/25 is the same as 1 over 5 squared. Of course, 1/5 is the same as 1 over 5 to the first. Now, 1 is the same as 5 to the 0. Obviously, 5 is the same as 5 to the first, etc. And 625, and you might have to think about this a little bit, is equal to 5 to the fourth. All right? So what we've got going on here is we've got 5 to the minus 2 plus 5 to the minus 1 plus 5 to the 0 plus 5 to the first all the way up to 5 to the fourth. So I can now say that this is the summation of 5 raised to the I power as I goes from -2 to 4. And that's it. All right. Now, probably the hardest thing about these types of problems is recognizing the pattern. Once you have the pattern and the regularity of the pattern, then it's pretty easy to translate that into a summation. All right? But it can be tricky. Definitely can be. Number 5. Which of the following represents the sum 3 plus 6 plus 12 plus 24 plus 48? Play around with this, maybe play around with the 4 choices, and see what you can figure out. All right, well, one way to do this problem is to literally take each one of the 4 choices and basically say, all right, well, does this particular summation give me this? Does this summation give me this? Does this one give me this? Does this one give me this, right? Do they work, The other way is kind of doing what we just did, which is to try to find a pattern and see if we can turn that pattern into a sum. Both of them are sort of equally valid. I'm going to try to go in that more forward route where I take this thing, try to turn it into a pattern and see what happens. Now, one thing that I noticed right away is that 3, 6, 12, 24, and 48 are all multiples of 3. And in fact, right, the first one is, no, that doesn't look right. The first one is 3 times 1. The second one is 3 times 2. The third one is 3 times 4. The fourth one is 3 times 8. And the fifth one is 3 times 16. All right. Now, what I should notice is that the 1, the 2, the 4, the 8, and the 16 are all powers of 2, right? They're all powers of 2. Specifically, this is 3 times 2 to the 0 plus 3 times 2 to the first plus 3 times 2 to the second plus 3 times 2 to the third plus 3 times 2 to the fourth. And once we have it there, it's pretty easy because we're always looking for something that's sort of going up by ones, and that's the exponent, right? 0, 1, 2, 3, 4, in which case all of this can be thought of as the summation of 3 times 2 to the I, where I starts at 0 and concludes at 4. And that happens to be choice 2. Now again, don't get me wrong. Another way of doing this is to take each one of these, using their definitions, start to write out their terms, and see if you get this 5-term sum. If you don't, then obviously it's the wrong choice. And if you do, then it's the correct choice. But I kind of like to work it through this way so that we really kind of review powers and patterns and things like that. All right, let's do one more problem. An interesting summation. Exercise number 6. Some sums are more interesting than others. Determine the value of the summation as I goes from 1 to 99 of 1 divided by I minus 1 divided by I plus 1. Show your reasoning. This is known as a telescoping series or sum. All right. So what I'd like you to do is I'd like you to start writing this sum out and see if you can find any kind of cool way of being able to calculate the answer without having to sum all 99 terms. See what you can do. All right, well, let me write it a little bit bigger, as usual. All right, so we're going to have the summation of I equals 1 to 99. You know, it seems like, wow, this is going to take forever. And it certainly would if you sort of did it directly, but let's do it. So the first one, you know, would be 1 divided by 1 plus, well, I guess, oh, sorry, not plus, but minus 1 divided by 2, right? Then I bump I up to 2, and I would get 1 divided by 2 minus 1 divided by 3. And then I would bump up I again, and I would get 1 divided by 3 minus 1 divided by 4 plus dot, dot, dot. And then my final one, right, would be 1 divided by 99 minus 1 divided by 100. Now, addition has this fantastic property. It's called the associative property. And the associative property says if I'm adding a bunch of numbers together, and I know you might be thinking, but there's some subtraction going on there. Well, that's okay. I can think of this as 1 plus negative 1/2 plus positive 1/2 plus negative 1/3 plus positive 1/3 plus negative 1/4. I can regroup the addition. So I'm going to regroup this in a very sneaky way. I'm going to do this as 1 plus negative 1/2 plus positive 1/2 plus negative 1/3 plus positive 1/3 plus negative whoops, that is just not going to get in there, negative 1/4 plus positive 1/4 plus etc. And then I'm going to eventually have negative 1/99 plus 1/99 minus 1/100. Now, what is the advantage of doing that? Well, 0, 0, 0, 0, 0, 0, 0, right? This entire sum goes, all of those terms in the middle collapse on themselves except for the number 1 and the number negative 1/100th. So all of this is equal to 1 minus 1/100th, which is 99/100ths. And that is our final answer, or 0.99, if you will. All right, anyway, that's a very, very special type of series or sum that we won't see a lot in this course, but it's kind of cool. It does come up a little bit here and there in calculus. Anyway, let's summarize, right? Now, what we looked at today was probably brand new to you, right? It even introduced you probably to a new Greek letter that you hadn't been aware of, right? This thing that looks like kind of a twisted and cool looking capital E, but in fact is the sort of equivalent of a Greek capital letter S, right? It's the capital letter sigma, and what it represents is a sum. And the way sigma notation works is basically says, hey, start with this integer, end with this integer, and then sum the terms that are generated by this explicit formula, all right, between those two integers. It's not too bad to do, right, especially when you're going in the forward direction. It gets a little bit more confusing when you're given a sum and you're asked to put it in sigma notation. All right, that can be tricky mostly because that's not ever a unique thing. You can always do it in many, many different ways. You've just got to be able to find a pattern that you can utilize to create that sigma notation. All right, well, we'll definitely see this notation for the rest of this unit. For now, I just want to thank you for joining me for another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.